All right, welcome to Unit 9, where we are going to be, in the first section, taking a look at comparing two populations, two proportions, or two groups. So in this case, in this section, Chapter 9, basically we're going to be taking what we learned in Chapter 8 with tests of significance, and now we're going to be comparing two means, two proportions, in order to make a stronger case for our inference. So after this section, what you'll be able to do is describe the shape, the center, and the spread of the sampling difference distribution of the difference of two sample proportions, determine whether the conditions are met for doing inference about P1 minus P2, we're going to take a look at constructing and interpreting a confidence interval to compare two proportions, and then finally we're going to perform a significance test about two proportions. All right, so we're going to just take the knowledge that we have learned from previous sections and just kind of combine it into this section to take a look at two proportions. So let's say we want to compare the proportions of individuals with a certain characteristics in population 1 and population 2. So in this case, we're actually taking a look at two different populations. Let's call these parameters of interest P1 and P2. The ideal strategy is to take a separate random sample from each population. Okay, so notice that the populations of interest are actually independent, and then compare the sample proportions with that characteristics. So what if we wanted to compare the effectiveness of treatment 1 and treatment 2 in a completely randomized experiment? So these two are a little bit different, just in the sense that we're taking a look at population 1 and population 2, so a population from Fairfax County and maybe a population from Loudoun County, two different populations. And here we're taking a look at treatment 1 and treatment 2 in a completely randomized experiment. So instead of the populations being independent, the treatments are actually independent of each other. So there's two different ways to be independent. So this time the parameters P1 and P2 that we want to compare are the true proportions of successful outcomes for each treatment. Okay, so we can compare the treatments as P1 and P2 and each population as P1 and P2. We use the proportions of successes in the two treatment groups to make the comparison. So let's just take a look at what it looks like when we have two different populations or two different treatments that we want to compare, how the notation is going to look just a little bit different than what it did in the previous section. So let's say that we either have independent populations or independent treatments. So treatment 1, the parameter 1 would be P1, so that's the population proportion. The statistic would be P hat 1, that's the proportion from the sample, and the sample size is N1. The population or treatment 2 would just say the parameter or the population proportion 2 of the second population or treatment. Just note that there's a 2, P hat 2, that's the statistic from the sample proportion, and then your sample size is N2. So now we're just denoting our treatments or our populations with a 1 and a 2 to show that there's actually two independent populations or two independent treatments. So what we're going to do is we're going to be able to compare the populations, two independent populations or two independent treatments, by doing inference about the population, about the difference between the two parameters, P1 minus P2. The two parameters are from two different populations or one group split up into two groups. Okay, we'll talk about what that means. Now, notice, to perform inference, we're comparing the two parameters. Once again, we don't look at the samples, we're taking a look at the populations. The statistic that estimates the difference between the two proportions is P hat 1 minus P hat 2. So in order to use P hat 1 minus P hat 2 for inference, we have to understand what the sampling distribution is going to look like. So hopefully you've said, hey, wait a second, this sort of actually looks like what we did in matched pairs, where we were actually subtracting, we were finding the differences and then finding the mean of just the difference. Well, why don't we do that here? Why don't we just subtract the proportions and then find what the mean difference is? The difference in this case is that I have two completely different populations, or I have two completely different treatments, so I can't just subtract the differences and find it, because that would assume one population, and in this case I'm going to have two independent populations. Okay, so let's take a look at what the sampling distribution is going to look like between two proportions. So to explore the sampling distribution of the difference between two proportions, let's start with two populations having a known proportion of successes. So let's say we're taking a look at school 1, and we know that 70% of the students did their homework last night. We're going to take a look at school 2. We know that 50% of the students at their school did their homework last night. Let's say that the counselor at school 1 takes a simple random sample of 100 students, records a sample proportion that did their homework. That's going to be p hat 1. That is the proportion from the sample. School 2's counselor takes an SRS of 200 students and records the sample proportion that did their homework. Okay, that's going to be p hat 2. What can we say about the difference p hat 1 minus p hat 2 in the sample proportions? Okay, did more students at school 1 do homework than students at school 2? Did they do the same amount of homework, or did students at school 1 do less homework than students at school 2? Now notice that the simple random samples are different sizes, 100 versus 200. That's okay. Okay, don't worry about that, because in the end we're just going to be finding the proportion and having like a decimal answer, so don't worry about the fact that the sample sizes are 2 different sizes. All right, so what we did was we generated below, here's some graphs. We generated a simple random sample of 100 students from school 1. That's this one right here. Okay, that's where our population was 70% of the students did their homework. Here's your standard deviation. Okay, same formula we looked at before. This one down here is a simple random sample of 200 students from school 2. So each one of these dots is a simple random sample, remember, of 200 students. Okay, where the population proportion was that 50% did their homework. Okay, so notice p hat 1, p hat 2. Take a look at that standard deviation. Now, what we did for the third one, okay, is we took both of these and we subtracted them. Okay, we took p hat 1 minus p hat 2, okay, and we subtracted the 2 sampling distributions, and this is now what our sampling distribution looks like. Okay, now let's just take a look at the center of this one. The center of the sampling distribution, where I subtracted p hat 1 minus p hat 2, is 0.2, and the standard deviation is 0.058. And we're going to take a look at how these are related, okay, to these 2 sampling distributions right here. Maybe you see something in there that's easy to recognize. Okay, so what do you notice about the center of the shape and the spread of the sampling distribution when I subtract them? So basically what this did is, this is basically I took every single sample and just subtracted them from each other to get this new sampling distribution right here. So this has 1,000 outcomes, this has 1,000 outcomes, and this also has 1,000 outcomes. Okay, so what do you notice about the center shape and spread of the sampling distribution of p hat 1 minus p hat 2? All right, let's take a look at them. Notice this sampling distribution is approximately normal. This makes sense because the first one was approximately normal, the second one is approximately normal, so when I subtract the 2, I would expect to get something that's also approximately normal. Now, this is centered. The mean of this sampling distribution is 0.2, so that's basically like saying when I subtract the 2, the difference is 20% of, there's a 20% difference in the amount of homework done by school 1 and school 2, okay? Now notice here, this was 0.7, this was 0.5. When I subtracted them, my new mean is 0.2. So the mean of the sampling distribution came from the subtraction of the 2, okay? Now let's take a look at the spread. So the spread here, 0.0458 and 0.0354. Ooh, when I subtract those 2, I definitely don't get 0.058. All right, the spread is a little bit different. Now hopefully you remember from previous sections when we combine random variables, how do I find the new standard deviation or the new variance from the combination of 2 random variables? Okay, so remember in chapter 6 we learned that for any 2 random variables, the mean, when I combine them, if I subtract them, I just subtract the 2 means. So if I have 2 means and I'm subtracting them, okay, I subtract the mean of x and the mean of y, and that gives me the mean of the combined distribution. However, remember, in order to find the new standard deviation of x minus y, okay, this right here is the variance, I had to add the variance of the first distribution, the variance of the second distribution, and then take the square root, and that will actually give me the standard deviation of the new distribution. I can't just add the 2 together. So let's choose a simple random sample of size n from population 1 with proportion of successes p1 and an independent SRS of size n2 from population 2 with a proportion of successes p2. Okay, so that's basically, that's just saying, okay, I have population 1 is independent from population 2. Okay, so how will we know when it's approximately normally distributed? So you're going to do the same thing that you did in your previous sections. You're just going to take the sample size times the proportion, the sample size times 1 minus your proportion, the second sample size times the second proportion, and the second sample size times 1 minus the second proportion. As long as those are at least 10, the sampling distribution is approximately normal. So same condition, you're just doing it twice, okay? The mean of the sampling distribution is just your, since we're talking about a difference, you just subtract the two proportions, but the standard deviation is a little bit different. So basically the standard deviation, let's take a look here. This, notice how this is the standard deviation of the first proportion, okay? This is the standard deviation of the second proportion. So basically what we're doing here is we're finding the variance and then taking the square root to get the standard deviation. So underneath here I have standard deviation 1 plus standard deviation 2, taking the square root. That is going to give us the standard deviation of the sampling distribution, of the difference of the two proportions. Just make sure that the population is still 10 times the sample size. Okay, so here's what your sampling distribution between two proportions look like. This is when I actually subtracted them. The mean is P1 minus P2. The standard deviation, basically you add the two standard deviations together and then take the square root. That will give you your standard deviation of the sampling distribution. Okay, so let's just take a look at an example. Back to our question from one of the first slides where we were talking about the two different schools and the percentage of students that did their homework in school 1 versus school 2. All right, so how could we describe the center, the shape, and the spread of this sampling distribution? So rather than just look, if we didn't have that picture to show us that it was approximately normal, how would we know it's approximately normal? Well, I'm going to take N1 times P1 so that we know that the first school had a sample size of 100 and the proportion of successes was 70%, so 100 times 0.7, and then same thing, the proportion of basically failures, so N1 times 1 minus P1, so 100 times 0.3 gives me 30. Now take a look at the second sample separately. I want to take 200 times 0.5 since 50% did their homework, and then 200 times 0.5 since 50% did not do their homework. So since all of those are at least 10, and you have to check both of them and you have to show the numbers plugged into both of them, the sampling distribution of P1 minus P2 is approximately normal. Okay, so what is the center? The center is the same thing as the mean. So I'm just going to subtract the two proportions, population proportions, to find the mean of the sampling distribution of the differences. Okay, so 0.7 minus 0.5 is 0.2. And then the standard deviation is just the combination of the two standard deviations together and then taking the square root. Okay, now what if we want to actually measure the difference between the two proportions? So how different are they really? We can do this in one of two ways. One, we can create a confidence interval to find a possible range of values that estimate how far apart the two population proportions are. Okay, so remember, a confidence interval is actually going to give us a range of values where the true difference in the two proportions can actually be. We can complete a two-sample test of significance to see if the two proportions are the same, different, one is more, one is less. Okay, schools did the same amount of homework, one school did more, one school did less. All right, so since we have two independent samples, the notation is going to have to look a little bit different than it did in the previous sections. Okay, so this is what we did at the very beginning. This is just showing that we're going to now put a 1 or a 2 next to my p values, my x values, my p hat values, and my n values to show which population I'm looking at, either population 1 or population 2. Okay, now there's still going to be the same conditions that we use for a one sample confidence interval. Let's say we want to use a confidence interval to check it. However, now we're checking the difference between the two proportions. So what do the conditions look like if I'm going to use a confidence interval for a test of significance using a confidence interval? Now, remember the confidence intervals always use the sample proportion. Always, 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 because that's all we have. We're using the sample to estimate the population. All right. For the simple random sample, you must have a simple random sample of data set 1 and data set 2. So two samples, everything you're just doing twice. For the independence condition for that standard deviation, you have to check both populations of data. The population of data 1 has to be 10 times the sample size. The population of data 2 also has to be 10 times the sample size. Then for the normal condition, once again, double check. You have to check that the first one is approximately normal and the second one's approximately normal. So both of them are approximately normal. When I combine them, the difference is also going to be approximately normal. So instead of doing 1 now for each of your conditions, you're just going to do 2.